what data is similar?
The location and the mass.
Okay, so the good thing is if a neutron did turn into a proton, at least it's in the same spot, and it's found where? In the nucleus. Good, I like it. That's a good start. Group 3, thoughts? What up here might support that a neutron could turn into a proton? Which is heavier, a proton or a neutron? A neutron, right? Is it a lot heavier? No, we're talking like what, 2,000ths of a 10 to the negative 24th grams? Okay. Group 4, does an electron weigh very much? No. If you look at the ratio between this number and this number is about 1,800 times bigger than this. So in other words, this is about maybe 2/1000ths of the mass of a neutron or a proton. So group 5, if a neutron chipped off the tiniest little piece of matter, it would weigh less, correct? And what weighs less than a neutron? A proton. So it seems like from a mass perspective, this seems reasonable. We say that a proton and a neutron have the same mass. If you look at the atomic mass unit, they're relatively the same mass. So that's why when we add protons and neutrons together, we get mass. Do they technically weigh the same amount? No. Protons weigh just like 2,000ths of a 10 to the negative 24th gram less than a neutron. So it makes sense that if a neutron chips off a tiny little beta particle, it's going to weigh a tiny bit less. And what weighs a tiny bit less than a neutron? A proton. Group 6, from a charge perspective, if a neutron loses something that's negative, it would become what? It would become positive. Well, what's positive? A proton. All right, well, that seems to make sense. It seems like the charge holds true, and it seems like the mass holds true. So it's really not that outlandish to think that if a neutron becomes unstable and ejects a beta particle, then it could actually turn into a green particle, which is a proton. How cool is that? Yeah, that's like nuclear physics going on there. That's awesome. Now, that's beyond the scope of this course, so we're really not going to talk much more about that. But any questions on how that is actually possible? So this class talks about things that are even smaller than atoms. We talk about protons, neutrons, and electrons. If someday you take a particle physics class, you'll talk about the stuff that makes up protons and neutrons. Those are called elementary particles, or quarks. There's up quarks, there's down quarks. They're really kind of quirky. They're so weird that they call them flavors of quarks. Again, that's beyond the scope of a chemistry class. So again, I will save that for a particle physics class. But it is totally feasible that that could happen. So let's go ahead and take a look at your answer key up here. So you had to do 2, 4, 6, 8, and 10. Give yourself a little score out of 5. How many of these 5 problems did we get right? Go ahead and discuss any ones that you got wrong with your small group members and see if you can work out any of the mistakes. Ryan, do you have your page 14 I can see from yesterday?
Was that the graph thing?
It's
like where you multiply them and
Yeah, do an average atomic mass.
Yes.
Oh, sweet.
How many did you have to do?
Oh, 5. I missed that. Oh, perfect, cool. And then just put atomic mass units on all those. Okay. AMUs. All right, quick show of fingers. How many out of these 5 did we get right? Sweet. Good. Awesome. Ones we want to go over. An alpha particle decay equation shows that the mass always goes down by 4. The proton count always goes down by 2. And then in a beta decay, because you're subtracting a -1, it actually goes up by 1, and the mass stays the same. Questions? So if you're trying to answer yesterday's essential question, which is the same as today, right now you know 2 out of the 4 main types of nuclear reactions. Alpha decay reactions are one type, and beta decay reactions are another type. Today, as we take a look at slides 50 through 57, we'll get into fission and fusion reactions. All right, so let's first of all even talk about why atoms might be unstable. Why do they decay into alpha particles and beta particles? Why might they go through fission and fusion? So, based on this graph, what makes an atom stable or unstable? So go ahead and discuss that in your small groups. Christian, when would be a good time to make up your lab quiz?
Is that the school?
Pardon?
After school.
You would do it after school?
Yeah.
Sweet, let's do it. Group 7, what are your thoughts? What would cause an atom to be stable or unstable? Like I see this belt of stability up there. So therefore, elements or isotopes in that belt of stability are probably stable. What's special about those elements in that belt of stability? Group 7. Ella, you want?
The ratio of neutrons and protons.
Yeah, the ratio of neutrons to protons. For elements in that belt of stability, do they have more neutrons or more protons? Like everything starts out with a 1-to-1 ratio. They have the same protons and neutrons. As you go up and up and up, eventually they have more and more what? More neutrons and more protons. Jordan? More neutrons. Quick conversation in your small group. Why would it be advantageous for a nucleus to have more and more neutrons? What about the neutrons would make that nucleus stable? Group 2, thoughts. What's so special about a neutron? I thought they were neutral. How would they make an atom stable? Okay, because they're neutral. All right. me more. Like down here, with 10 protons, 10 neutrons is a stable species. Let's draw a picture of that. Protons and neutrons are found where? In the nucleus. So here's this nucleus. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neutrons. That's stable. That's not going to blow apart. That's not going to shoot out alpha particles or beta particles. Can you give me an example, group 2, of a nucleus that is unstable with a 1-to-1 ratio? When does this 1-to-1 ratio no longer meet up with the belt of stability? How many protons do I need? 20. I'd say that's just on the verge of being stable. I think that 1-to-1 ratio is probably still in that belt of stability. Maybe 40? Right there? 40 protons, 40 neutrons isn't in that belt of stability. So let's draw that picture. I already did 10. Let's go 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right, and I need 40 neutrons as well. So 10, 11, 12, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right, there is a 1-to-1 ratio. 40 protons, 40 neutrons. Quick conversation in your small group. Why might that be unstable? It's too much to handle. Too much to draw. Group 3, why might this be unstable? What's bad about this picture? I'll give you a hint. What charges are attracted and what charges repel? Opposite charges attract. Do we have any negatives up here? No. I mean, electrons would be attracted to the positives in the nucleus, but we're not talking about negatives up here. Group 4, tell me what positives do to positives. They repel. Do you see a lot of positives up here? Yeah, I see 40 positives. So there's going to be a lot of repulsion up here. So why would adding an extra 10 neutrons make this more stable? Group 5. We know positive protons repel positive protons. There's a lot of repulsion going up on here. Why would adding 10 extra neutrons make this stable? Give you okay. And if you've ever had to sit in like the back seat of the car, are you going to sit next to your sibling on a big road trip or sit as far apart as possible? Maybe putting like a stuffed animal or a TV in between. Yeah, you're going to try to separate that repulsion. I don't know about you, but sometimes siblings do not get along, especially on a long road trip. So you're not going to, like if you have 3 seats in the back of the car, you're not going to put people right next to each other, right? You're going to put them as far apart. I guess I should put positives here. As far apart as possible with like a neutral mediator in between. Well, guess what? Neutrons are neutral. Even though there's no attraction or repulsion, they're going to add some extra space in between some of those protons. Plus, there's this thing called the strong nuclear force that it's kind of the glue that holds the nucleus together. By adding extra mass, you're going to get extra nuclear force there. But you can basically think of those neutrons as neutral mediators separating some of those positives. The farther apart the positives are, the less repulsion there is. Any questions on that? So that's why when you look at the periodic table, helium has 2 protons and the mass is double that. It's 4, because 2 plus 2 will be 4. If you take a look at beryllium, it doesn't take very long before you start to realize that you have extra neutrons. Beryllium has 4 protons. What would give you a mass of 9? Was it? 5 neutrons. It's no longer a 1-to-1 ratio. It's pretty close to a 1-to-1 ratio, but pretty quickly, by the time you get to element 4, you need an extra neutron in the nucleus to make it stable. You go up to here. Okay, maybe neon's okay. 10 protons, 10 neutrons, giving me a mass of 20. But by the time you're up here, maybe even calcium's okay. 20 protons, 20 neutrons gives you 40. But by the time you get like down here, it's no longer, like if this was double, that would be 86. Well, that's not going to be stable. You need a lot more neutrons to make it stable. Even here, double 47, you're going to get what? 94. You can see we have a lot more neutrons to make it stable. So those neutrons are in there helping to separate the positives to make it stable. Any questions on that? All right, let's get into our fission-fusion reactions. So fission, when you hear the word fizz, at least in my mind, like bubbling and fizzing in carbonated beverage, it's like something's breaking apart, kind of like baking soda volcanoes. Okay, it's fizzing, it's breaking apart. Well, that's exactly what's going to happen here. It's when a big, large, unstable nucleus is going to break apart into 2 smaller nuclei. So here's an example, uranium-235. It's a pretty big isotope. Now, it's not just going to naturally break apart. This N stands for a neutron. Would you agree it has a mass of 1 and it doesn't have any protons? It's a neutron. So we're going to shoot that neutron at this isotope. It's going to cause it to wobble, and then it breaks apart. What does it break apart into? Well, there's lots of options up here. So these would just be 2 examples of what it could break into. It doesn't have to be a perfect split, as long as 36 plus 56 adds up to 92 protons. It doesn't really matter which isotope of chromium and which isotope of barium it turns into, but in this case, when you add that up, you're going to get 133, 223, a mass of 223. Quick conversation in your small group. Why do I need 3 neutrons over here? Why do those 3 neutrons need to be on the right side of the reaction? Group 6, thoughts? I have 92 protons. If you add these 2 daughter isotopes up, you'll get 92 neutrons. If you add up the mass on the left here, 235 plus 1 is 236. Why do we need those 3 neutrons on the right? This right here is 233. What plus 233 would give me 236? Group 6? Oh yeah? Yeah, 3 neutrons. So this is just like the homework from the other night. You got to get your protons equal on both sides, and you have to get your masses equal on both sides. So the neutron is kind of like the extra stuff that helps the masses all work out. So the protons have to be equal on both sides. The neutrons, or the mass, when you add them up, has to be equal on both sides. Now this is a really important reaction because it took 1 neutron to get this reaction started. And I just spit out 3 neutrons. If those 3 neutrons hit more isotopes, would you agree that that's enough to start 3 more reactions? And then if those 3 reactions all spit out 3 neutrons, how many neutrons am I going to have? 3 reactions, each giving up 3 neutrons. 3 times 3? 9. And if each one of those 9 reactions give off 3 neutrons, how many neutrons is that? 9 times 3? 27? You can see how this can get out of control pretty quickly. 1 neutron gives off 3 neutrons. 3 turns into 9. 9 turns into 27. In a fraction of a second, this can go out of control, and that's basically what a nuclear bomb is. So this occurs in bombs and nuclear power plants. Now, the difference between a nuclear power plant is it's very controlled. Whereas in a bomb, you want it to go out of control pretty quickly. So these would be the types of bombs that were dropped on Japan in World War II. So these are called atomic bombs. Nowadays, we have hydrogen bombs, which is the next topic. That's fusion bombs. But these would be atomic bombs, nuclear fusion. Or sorry, fission. Now, how do we keep this from going out of control in a nuclear power plant? What would I have to change up here so that this doesn't go out of control? Quick conversation. That involves you talking to your small group members. I'll open it up to anybody. What would I have to do up here to stop this reaction from going out of control? Keep in mind, 1 neutron turned into 3. If those 3 neutrons hit 3 other uranium isotopes, that's going to turn into 9 neutrons. And then if those 9 neutrons hit 9 uranium isotopes, that's going to turn into 27 neutrons. What do I have to get rid of up here to keep this nuclear fission reaction under control? Like in 3 Mile Island or other nuclear power plants. What do I have to get rid of up here? Or what do I have to kind of hide? It's the neutrons, right? So what we do is in a nuclear power plant, we put in these absorbers, these rods that soak up these neutrons. If we need more electrical power, we lift the rods up. The neutrons start hitting more uranium atoms, and then it starts producing more power. If it starts to produce too much power, we put the rods back down in. I think they're made out of boron. That boron rod in there soaks up these neutrons so that they can't hit uranium. So if you've ever seen National Lampoon's Christmas Vacation, when Clark Griswold plugs in his electrical outlet, and he basically wipes out the electrical grid, they flick on the auxiliary power switch to get more electrical power at the power plant. They're lifting up those boron rods, allowing more neutrons to hit more uranium isotopes. That creates more neutrons, more reactions, more electrical power. So that's basically how you keep it under control. Or in a nuclear bomb, there are no absorbers. You want it to get out of control pretty quickly. Questions on that? So now if you just take a look down below here, this is the same exact reaction. We have uranium-235 by a neutron. Notice how the 2 products can be totally different. How that unstable nucleus splits apart, that's just random odds. So I could split it into 36 protons and 56 protons. You could just as easily split it into 38 protons and 54 protons. It doesn't really matter. These are 2 specific isotopes. So when we add this together, we get 234. But now we have to get that to add up to 236. So in this case, there'd only be 2 neutrons. So again, it's all based on random odds, what it turns into. You have millions and billions of these reactions happening every second. So there's a lot of products. One thing to keep in mind is these final products are radioactive. So like in 3 Mile Island, when it was still up and running, those final products had to be stored properly because these isotopes are going to continue to decay for thousands of years. They'll be radioactive for thousands, if not tens and hundreds of thousands of years. So that's one of the downsides of a nuclear power plant or a nuclear bomb. When you drop nuclear bombs on like Japan, not only did that kill a lot of people, but in the years following, there's a lot of radiation just kind of wafting around Japan. Lots of people died of leukemia and other causes. So there are some long-term consequences associated with this. Any questions on fission, breaking apart, often caused by a neutron being hit into the isotope? Questions on that? All right, so let's do one example here. We have uranium-235, 92. This is on page 18. This is like one of the first problems from your homework today. So we're going to hit it with a neutron. And one of the products is lanthanum-57. So there's 57 protons. How many protons do I need here to add up to 92? Twelve minus 7 would be 5. 8 minus 5 would be 3. Just add it back and make sure that's true. 7 and 5 is 12. Carry the 1. 3, 4 plus 5 is 9. Yeah, I think we're good. Which element has 35 protons? Br, bromine? Perfect. Over here, I have a total mass of 236. So on the right-hand side, I'm going to need a total mass of 236. Well, here's 138. 3 neutrons would have a mass of 3. So right there, I'm up to what, 141? How much more mass do I need to get up to 236? 5 would put me at 146. So 90? Does this seem reasonable? 6, 23. Yeah, so the final answer would be bromine 95. Does that make sense how the top numbers have to add up on both sides and the bottom numbers have to add up on both sides? So I'm going to give you every piece of the equation except for the missing piece. Yeah, it's just kind of like a little Sudoku puzzle. Any questions on that? All right, so now you have 3 out of your 4 main types of nuclear reactions. So we have alpha decay, we have beta decay, we have fission, which means breaking apart. Our last one would be, yes, you got it right. Our last one would be fusion. When I hear the word fuse, it means coming together. Like you can fuse or weld 2 pieces of metal together. Sometimes when people have spine issues, they fuse 2 of the vertebrae together so they're not bending and sliding past each other. So fusion means sticking together. So this is where 2 smaller nuclei come together to form a larger nucleus. This is how stars make elements. They sometimes say you're just made up of stardust. Well, this is actually how we get bigger elements. When hydrogen on the sun joins up with hydrogen on the sun, and under all that heat and pressure, you get 1 proton plus 1 proton going together, you're going to get 2 protons. Is 2 protons still the element hydrogen? No, now that's going to be the element helium. And then once you get enough helium on the sun, helium could join up with hydrogen to form 3 protons. Well, that would be lithium. And you can keep going. You can add 2 heliums together. 2 plus 2 would give you 4. That would be beryllium. That's basically how we get all the elements on our periodic table. Stars start putting these elements together. This is how a hydrogen bomb works. A lot of times people mix up atomic bombs with hydrogen bombs. They're all nuclear types of bombs, but this is basically what led to the Cold War. We started making these hydrogen bombs. Luckily, we didn't drop them on anybody, because then the Soviet Union probably would have dropped them on us. They started stockpiling nuclear bombs down in Cuba. We had the whole Bay of Pigs controversy, all that sort of stuff in the 1960s, 1970s. So yeah, that basically is what led to nuclear proliferation. We did drop in a hydrogen bomb somewhere in the Pacific Ocean. There used to be an island there. I think it was called the Bikini Atoll. That hydrogen bomb was so powerful, way more powerful than a atomic bomb. It basically wiped the island off the map. It's not there anymore because it was that powerful. I think the Soviets launched one up in the Arctic Circle somewhere. So yeah, we have launched them before, but luckily no one has ever dropped them on another country. The cool thing about hydrogen bombs, well, not hydrogen bombs, but stars, and fusion is the products are, they're not dirty anymore. They're not radioactive. So if we could ever get a fusion power plant up and running, and we could actually get it to produce more power than what we have to put into it, that would be pretty cool, because the final products wouldn't have to be stored as being radioactive for thousands of years. Any questions on that? Putting two protons together to get two protons. All right, so let's go ahead and take a look at example. I don't think this is example 1. It's on page 18. Maybe this is example 3. Oh no, that is number 1. Well, I guess the last one we did was 3. So this is number 1 here. All right, so we have 1 proton and 11 protons. You put those together, how many protons do you get? 12? And if you look at the periodic table, 12 would be which element? Mg? And we have a total mass of, what is that, 25 on the left? We have to, here's a mass of 1, so I'm going to need a mass of 24 plus 1 would give me 25. So the final answer to this would be magnesium isotope 24. 2 elements going together to form a bigger one, plus maybe some extra neutrons just to help all the mass work out properly. Any questions on that? So your, yep.
What is that neutron? That just naturally happens.
It just naturally happens, yep. Oftentimes, there's certain rules to which isotopes you can form. That's way beyond the scope of this class. That's like a nuclear chemistry class. But basically, maybe isotope 25 doesn't exist. So isotope 24 can exist, which means it's going to shoot out a neutron. Does that make sense? Okay. So yeah, you just have to get your masses and protons adding up on both sides. So that pretty much wraps up the notes for today. So your homework is page 18. You're going to do the even problems. So 2, 4, 6, 8, 10, 12, 14, 16, and then don't forget about question 18. Any questions on that? All right, I was going to have you do the pre-lab as well, but based on how much time we have, I think we'll have enough time tomorrow that in your small groups you can work on the pre-lab. The cool thing is before we leave for break, we're going to do an actual nuclear radioactive lab. So I'm going to put out radioactive samples. You're going to use Geiger counters to measure the radiation being given off by those samples. It's pretty low-level radiation. It's pretty safe. I mean, I wouldn't sniff it or like get it close to your face or anything, but as long as we take the necessary precautions, we'll be able to do the lab, measure the radioactive particles. So we'll do the pre-lab at the beginning of class. So even though Google Calendar says you have a pre-lab due, we'll take care of that first thing tomorrow. As long as you have page 18, the evens done, we'll be good to go. Jams, any questions from home?
No, I'm good.
All right, so again, the pre-lab, which said it was going to be due on Google Calendar, I'll scrap that. We'll work on that tomorrow. Do you have a buddy that lives close to you that could pick up a hard copy of the pre-lab, or are you just going to fill it out digitally?
I can just fill it out digitally. That's fine.
All right, so you'll find that tomorrow on the front cover of your unit packet. You'll just work. I'll wheel you over to Christian and Brady if he's here, and you can work on that pre-lab together.
Okay. Sounds good.
So page 18, the evens is homework.
Okay.
All right, have a great day.
You too.